Hello, everyone. Can you hear me? Is the voice okay? Can you hear my voice? Okay. Let me share my screen. Can you all see the screen? All right. Okay. Very good. All right. I'm gonna give 1 minute in case more people join. 5 people here. So today we're gonna go over the solution of 3 homeworks. We're gonna go work backwards from homework 3 back to homework 1. I'll wait till 3:50. I think that's a normal start time for the class. I think more people may come online that time, about 3 minutes. You guys can just relax and get a coffee or something. Okay, it's 3:50 now. Let's get started. So I'm gonna work backwards from homework 3 back to homework 1. So homework 3 is a practice of micromechanics, predicting laminar properties from its constituent properties. So the problem is here. Let me minimize this. How do I minimize that? There we go. Okay, as you can see, it's a lamina of graphite fiber, epoxy matrix. Fiber volume fraction is 70%, so the matrix is about 30%, assuming no porosities. Fiber is hexagonal packed. This is relevant for Halpin psi equation. Use the data table in the previous 2 slides, which means this 2 slides here. This slide and this slide to calculate the mass fraction of the graphite and the epoxy. I mean, the first part is the easiest because we know the density information. Density information is given here. Specific gravity. Usually the reference is water. So if something has a density of 2.3 and water density 1.1, so this ratio is a specific gravity here, right? If you can look it up, that's usually what it is. So graphite fiber here, in this case, is 1.8 density of water, and then epoxy is 1.2 times the density of water. Okay. So to calculate their mass ratio, you just need to use you want to calculate the mass of graphite ratio mass of matrix, right? Matrix, which is the volume of graphite times density graphite versus volume of matrix times density of matrix. Okay. And then you just plug and chug. You can just use you can replace density with a specific gravity because the ratio doesn't matter. The reference density cancels out, right? You just multiply. The graphite, you can assume total volume is 100. The graphite will be 70. Matrix will be 30. You do 70 multiply the specific gravity of graphite, 30 multiply the specific gravity of matrix. You calculate the ratio, right? So it's pretty simple. It's end up to be 3.5 to 1. To 1. This is the first part. Any question about the first part? You got the same number? You can unmute yourself. You want to speak up, you unmute yourself, you can talk.
I didn't divide the matrix by the fiber, but I did get the numbers that would make that work.
Why you divide? You want to modify, right? It is,
well, I'm saying I've got the 2
kilogram.
numbers that would have made it 3.5 to 1, but I didn't set it as 3.5 to 1.
So what's the number you got?
I've got 0.778 and 0.222. I didn't convert it over to a ratio.
Oh, that doesn't matter. That's okay. Yeah. So if you divide those 2 numbers, you put a ratio. It should be the same number. I'll check the ratio. If the number has same ratio, that's correct. Sounds good.
Good.
All right. The second part is estimating a bunch of modulus, right? Longitudinal means along the fiber. Transverse means perpendicular to fiber. Implant shear. Use both rule mixture and Halpin psi equation. Okay, this is the second part. So basically in this part, we basically practice these rule mixtures and Hoping-Tsai. The rule mixture has two forms. If you remember, there is a void form and then rules form. So void form is for things in parallel. When you do when you have these element function in parallel, you use void model. When you have things in series, you do a rules model. Okay. So when you talk about the stiffness in the fiber direction, your fiber and the matrix are essentially in parallel. But you load this way. They're a parallel element carrying the load. So you should use void model. When you calculate the modulus in two directions, this directions, your fiber and the matrix in between fiber is the series. So should use a Roos model. Same thing happens when you calculate in-plane shear. When you have shear situation that like this, when you have shear, what happens? They each one of them shear. They're in series. The shear add up. So shear these add up. So that's also Roos model. Okay. So this is a big picture. The choice of models. Usually the E1, the modulus in the fiber direction, is the easiest to estimate. This equation gives you a pretty accurate measurement for pretty much all composites. And the E2 and G12 are the difficult models. The Roos model is a crude estimation, and the better estimation is the Hoping-Tsai equation. Hoping-Tsai equation is an empirical equation. That's over here. Oops. Where is it? Here. Okay. So there's Hoping-Tsai equation for E2, and there's Hoping-Tsai equation for G12. So use this part for E2, I use that part of G12. So there's some parameters we need to determine. One of them is Kc. Kc has to do with the volume fraction and packing. So the problem, the given condition, the problem is hexagonal packing, high volume fraction, 70 is pretty high. So for E2, Kc equal to 1, right? For our problem. Then we need to use Kc to calculate eta. This Kc go into here. We know these numbers, we calculate eta. And then eta goes into here and Kc goes into here. Volume fraction goes in here, and then we know this number. This number is matrix modulus. So this is a general steps you go for. You go from Kc to eta, and everything goes into the final one. The important to know is that when you calculate E2, you got to use the transverse Young's modulus. You calculate this ratio, EF to EM, using the transverse Young's modulus, because for graphite fiber is quite different. The Young's modulus for graphite fiber has two numbers. One is this number. This number is along the fiber direction. The other number is perpendicular fiber or transverse modulus. So when you estimate E2 of the composite, this number is the one you want to use. Okay. A few important points. Okay. So I did my calculation using Excel. So I basically this is the E1 estimation is a void model. This part. Okay. It's basically this number is the fiber modulus in one direction. I call it EF1. Can you see my screen, Excel screen?
Yes.
Okay, so I make it a little bigger. All right, this is a matrix. Matrix is isotropic, so it's the same modulus for all directions. 3.4, this number here. Okay, and then fiber volume fraction, and then matrix volume fraction. Right. I just mix them with a voice model like this. This is the equation here, right? Basically, this number multiplies this number, and plus this number multiplies this number. It turns out to be 162 gigapascal, because I use the gigapascal as input. Okay. All right. And then I can estimate E2 using rule mixture. That will be Roos model, because it's series, not parallel. So I started with the fiber property, which is 22. Remember, 22 is this number right here, 22, this number. So the 22 goes here, that's fiber. Matrix 3.4 gigapascal. And then the rule mixture is the Roos form, rule mixture, which is inverse form. 1 over E2 equal to VF over EF plus VM over EM. Okay. And then I inverted it. I get this is a inverse of an inverse. Sum of inverse and inverse. That's the Roos model. This is the number 8.3 gigapascal E2 based on rule mixture. Okay, that's and then the E2 you can also apply Halpin-Tsai equation. Now I first calculate the coefficients. Psi is 1 for the reason we just described. It's a Higgs-Pack high volume fraction, so that's equal to 1. And this ratio that going to calculate eta is EF2 over EM2 is a fiber modulus in 2 direction versus matrix modulus. So it's a ratio of 22 is the ratio of these two numbers. Right, that turns out to be 6.7. And then this is the eta. Eta is the equation, Halpin-Tsai equation. What is that? Where is it? Eta is this number. This number is eta. So I calculate eta over here, and then this is the eta number 0.72, and then this is the final equation Halpin-Tsai to calculate E. I basically use this equation. I know EM is 3.4, so I multiply EM on the left and right. So this fraction, this ratio multiply EM is E2. So I got E2 is 10.5 gigapascal. Roos model usually underestimates things. It's give you the lower bound. So the Halpin-Tsai is slightly above Roos model. Roos model says 8.3. Halpin-Tsai says 10.5. It makes sense. It's bigger than Roos limit. All right. Any questions? All right, the next part is the in-plane shear modulus. Again, there are two methods. One is a rule mixture. In-plane shear is also series situation. You know, these things load in the series, they build up. So I can apply Roos model similar fashion, but I need to read off the shear modulus from the table. The shear modulus for the graphite fiber 22. The shear modulus for matrix 1.3 from the table. And then this is a Roos model based on the volume fraction, inverse of inverse. The sum of the inverse and inverse is 3.8 gigapascal based on rule of mixture. And then I can apply similarly Halpin-Tsai equation to do the same thing. The Halpin-Tsai equation for shear is this. The Cassie number is for shear is different than the Cassie for E2. So Cassie determined by this is 1 plus 40 times volume ratio, fiber volume ratio power 10. So when you calculate G12, you got to use this Cassie. This Cassie is slightly different than the Cassie for E2. So at first I calculate this, but I know VF is 0.7. So calculate the Cassie here. The Cassie is 1 plus 40 times this VF power 10. The Cassie is 2.113. Okay. Just based on this equation right here. Then I use a Cassie to calculate eta. Eta is here. Eta is the ratio of the shear modulus and the Cassie. You know, this ratio -1, this ratio plus Cassie, and the ratio of these two is eta. So second I calculate eta. Eta is here. This is the eta. This is -1 plus this, it's 0.83. Finally, I plug in eta and Cassie into this equation. This is shear modulus of matrix. GM is a matrix, and this is a whole bunch of parameters. Cassie, eta, and VF. VF is 0.7. Okay. Cassie is this number 2 point something, and eta is this number So plug everything in, you calculate G12. G12 is 7.06. Again, it's higher than the Roos limit, which it should be. It should be higher than the Roos limit. Any questions? Does it make sense to you? All right, the next question, the same part of the question. The next part is calculate the thermal expansion coefficient in one direction, which is fiber direction, and two direction, the transverse direction. So we basically exercise two equations here for thermal expansion. These two equations right here. These two. So this is rule mixture for thermal expansion. Alpha 1 is fiber direction. Alpha 2 is transverse direction, right? We just basically apply these. Alpha 1 is real simple. It's just fiber thermal expansion in one direction. Remember, the graphite fiber has a very weird thermal expansion behavior. It actually contracts. When you heat it up, it contracts, right? And then alpha m is the thermal expansion coefficient for the matrix. And typically polymer expands a lot more than fibers and metals. This is a huge number right here. But its volume fraction is low and its modulus low. And this fiber is weird number, but its volume fraction is high and modulus high. So this all balance out based on rule mixture. This E1 is the effective Young's modulus of the lamina in one direction. So this one is what you calculate in step 1. This E1 is the number we calculate here. This number, we got to use this number for that E1. Okay, so basically plug and chug. I calculate over here. And then this is the thermal expansion coefficient for fiber in one direction. The actual negative is negative 1.3. Okay. And the matrix is positive. The unit I use here is 10 to the minus 6. It's a ppm, part per million, basically. This is I can should say ppm. Okay. And this result is also ppm. Okay. So I basically plugged in. I did it. That's the equation I typed in. I type in basically this equation right here into the Excel, and I reference the data from previous calculation. So it turns out that alpha 1 is still negative. It's still dominated by the fiber in one direction. It's not as negative as this, but it's due to the contribution matrix. It's negative 0.9 or so. All right, alpha 2 is slightly complicated. So it involves these quantities, the fiber properties, matrix properties, and then that's the Poisson ratio. So you can calculate the effective Poisson ratio for the composite using the rule mixture, and that effective Poisson ratio goes into here. And then this is a matrix contribution, fiber contribution. Now, when you put alpha F here, this alpha F is the fiber thermal expansion in the two direction. Fiber thermal expansion in one and two direction are different. The graphite fiber has thermal expansion of 7.0 in two direction, not 1.3. It's 7.0 positive in the transverse direction. This is the number we should use for the transverse direction estimation. Okay. All right. So this is a 7.0 graphite thermal expansion in two directions. And this is the 6.3 for epoxy. Epoxy is isotropic. And this is all the Young's modulus. This is the effective Young's modulus for the composite. Not Young's modulus, this is Poisson ratio. This is a rule mixture of fiber and matrix. And this finally, this is the equation for estimating alpha 2. It's the equation here. It's equation here. It's this equation that I used. This one. You put everything in, turned out to be 31.2 in 2 directions. Again, you can see the 2 direction is a lot higher than 1 direction because the matrix contribution. Also because the fiber actually expands +7 in that direction. ppm. All right. Any questions? Make sense? All right. Let's see the problem. The last part of the problem is estimate the longitudinal tensile strengths. This is what we discussed. We also discussed the difficulty of estimating strengths. We basically can estimate this tensile strengths due to the fact that the longitudinal tensile strength is pretty much dominated by fiber. When the fiber give up, it's over. So we basically assume that if you stretch the thing to the limit of the fiber, we estimate the stress it takes to stretch the composite to the limit strain of the fiber. And that's the stress of the, that's how much this can take. So the equation for that estimation is here. This is the basic ideas. We assume that when you stretch the composite in the fiber direction, when the fiber reaches its failure strain, the whole composite is gone. And then we estimate what it takes to do that, what the stress it takes to stretch the fiber to its failure strain is this equation right here, based on the, again, rule of mixture. All right, so what we need here, we need to ultimate strength of the fiber, sigma f ultimate, volume fraction fiber, and the failure strain of the fiber, Young's modulus matrix, and then volume fraction of the matrix. This is what it takes to calculate. Now, this number, failure strain of fiber, is not given, but you can easily calculate the failure strain because fiber usually is brittle material. So you take its ultimate strength of fiber divided by longitudinal modulus fiber, and you get failure strain based on Hooke's law. So that's what I first estimated. So I take the failure strength of the fiber, which is 2060 megapascal, divided by its Young's modulus, which is 230 gigapascal. I estimate the failure strain of the graphite fiber, which is here. I basically take this strength right here, 2967, right? That's the actual tensile strength of the fiber only, divided by fiber Young's modulus 230 gigapascal. That indicates the fiber will fail at 0.9% strain. That's the 0.9% strain. That's epsilon f ULT in that equation. And then you just plug and chug, you plug other things in needed. This is a strain, this is a this is the equation. It turns out that it turned out to be, the composite strength is 1.4 gigapascal or 1446 megapascal based on this equation. Oops. This one. All right. Any questions? Okay, if no more questions, I'm gonna move on. If you do have questions, You can either type in the text box or speak up. Oops. All right, let's move on to the next one. I'm gonna close this. And open up the homework number 2. This homework number 2. What the heck? What is this? Close it. Oh, it won't let me open PDF. Let's use Word. Okay. Let's talk about the first one. The first one is basically given a motion, a displacement function, calculate strains, and make some sense out of it, right? So we have a set of equation we learned. So basically, we know that back to this. We know that this keyboard is in my way. Epsilon x is partial u partial x. Epsilon y is partial v partial y. Epsilon z is partial w partial z. Gamma xy is partial u partial y plus partial v partial x. Gamma yz is partial v partial z plus partial w partial y. Gamma xc is partial u partial z plus partial w. Right. This is what we learned in the class. So basically, if you know the motion, if you know, in a body, a point at x, y, z, it moves. It moves to another point. This motion has a 3 component: u, v, and w. U in x direction, v in y direction, w in z direction. Now, if you know these functions, the motion, this basically tell you for every point x, y, z, how does it move? How will it displace in the motion? If you know these 3 members, we can calculate strain. Just plug and chug. Right. So we basically just plug and chug. If you read the question gave you this function. The question gave you this. This is a function given u, v, w. All we need to do is just plug in, plug into the equation. So we calculate u epsilon x strains. Epsilon x is partial u partial x. It's actually partial x. Z times psi x xy. Right. Now we know the z doesn't depend on x, so basically it's z times psi x xy. Right. So this is the first derivative to x, and then we do another derivative, so that's xx. So that's the first string component. That's the equation for it. All right. Similarly, we can calculate epsilon y. Epsilon y is partial v partial y. So we do a partial y. Z times psi y xy. All right. I give you z times psi yy xy. Right. Any questions? Check your response. Okay. All right. And then epsilon z. Epsilon z is partial w partial z. It's partial z. And then the w function is w0 xy. It doesn't depend on z. So this function doesn't depend on z. That's equal to 0. All right. Then gamma xy is partial u partial y plus partial v partial x. And again, you plug and chug. You plug uv into this equation. It turns out to be 2 times z psi xy function xy. And gamma x z is psi x xy w0 x xy. And gamma yz is psi y all right. This is the 6th string component that you can derive from the given. You should apply this set equation from the set of conditions. This is 6 string components right here. All right. Now let's see what does it mean. So basically, if you think about a cross section of the plate is, this your xy in plane. So z is a perpendicular plane. So you have z, you have x. So your u function is basically z time so assuming there is a normal line to this plate. This is a normal to the midplane. Okay. Now, when this line rotates certain angle, like this, all right, and assuming this angle is this number here, and then your u displacement essentially a function of z. When z is above this neutral plane, it's positive linear, and when z below neutral plane, it's this plane, it's negative. So so this is in a way you can understand this as a rotation of the normal with respect to y-axis. Y is into the paper. This rotation angle is this function right here. Okay, and that give you a picture of the u function. V function is z time psi y xy. Now, if you look another cut in the yz direction, yz cut, you look across in the yz cut. That's y and this z, and you look at the normal. It has certain, assume it has certain rotation. And then the v function, this will be the v function. V function will be the z coordinates multiply this angle. So physically, this could mean the rotation of the normal with respect to xy axis. Okay. All right. And the w function is how much it drops. So this plane can drop. So this part can drop into this part. There's a vertical drop. That's w function. The rotation is this function. So if assume that there's a plate. All right. If you assume the in-plane stretching function is 0, this case essentially is the case given in problem 1, with the different signs depending on the direction of z. This is this negative. But you compare this to this. You assume the in-plane displacement 0, and then basically this motion is motion as you analyze in the problem. It's basically it's a motion of unstretchable. You assuming a plate with a midplane was unstretchable, but it can bend. You can deflect and bend, but you cannot stretch. There's no stretching. Okay, and then this motion described is will result in this strain here. This strain, this part is 0, unstretchable, and these are the strains. The strain is purely due to the rotation of these normals. So your result actually indicate this is 0, this is 0. This is your x strain, that's your y strain. Okay, and that's your gamma xy strain right here. This also drop out. This is the relationship of that problem with this problem. So this is a special case of this general motion for plate theory. And this is the psi function. All right. Any questions? Okay. All right. No more. If no questions, I want to move on to the second problem. Second problem is given a string tensor, find the principal string. Okay. And the principal direction are orthogonal, basically. So what need to be done essentially is just calculate eigenvalue, eigenvector of that matrix, basically. So I'm gonna write up here. The problem 2 is. So we basically we have a string tensor, which is 65, 33, 0, 33 minus 73, 0, 0, 0, 4, and I want to find the principal string. You can use any solver to do it. You basically you can use MATLAB to find the principal string. I just want to the principal. There's 3 principal strings are. This is 10 to the minus 4. So the principal string is, if you do after calculation, you find that principal string 1 is 67, 10 to the minus 4, and principal string 2 is 4, 10 to the minus 4. Principal string is minus 75, 10 to the minus 4. These are the 3 eigenvalues for this matrix. And turns out that these are the principal strings. If you interpreted the tensor as a string tensor, then these 3 eigenvalues are the 3 principal strings. Okay. And also you can figure out the principal direction for each one of them. So when you solve the principal string, you can invoke MATLAB or someone. They also give you the principal directions. It's a vector, usually a unit vector that actually signify a direction. So this direction is, the vector is 0.993, 0.12 and 0. This is for 1. This vector is 0, 0, 1. This vector is 0.12 minus 0.993 and 0. Questions? Do you get the same number? All right. So it's pretty straightforward. You just essentially figure out the eigenvalue, eigenvector of the matrix. And then the C part is to show that the principal string directions are orthogonal, but I mean they're perpendicular to each other. Now the way you show it they're orthogonal is you dot product the eigenvectors and show that they are perpendicular. So let's say this n1, this n2, this n3, these 3 vectors. You basically calculate n1 dot n2 and that's 0. You can calculate here that's indeed 0. You do n1 dot n2 n3 that's also 0. You dot this with this that's also 0. And then you dot n1 n2 n1 n2 n2 n3 sorry n2 n3. You pick any 2 of these eigenvector, you make a dot product, they give you 0 values. That means they're perpendicular to each other. When all the 3 conditions are satisfied, that means the 3 vectors are mutually orthogonal to each other. Indeed, they are. You can calculate pretty simply. They're orthogonal. Okay. Any questions? All right. All right, the third problem. Let's look at the third problem. The third problem is a string tensor. That's here. Find the normal string in the direction defined by this vector. You can verify this is a unit vector. Another vector is perpendicular than 1. Find the shear strain defined by n1 and 2. Okay. And find the principal strain and maximum shear strain. Find the volumetric and deviatory strain. So it's pretty straightforward. So let me lay out a general strategy to do this. So basically, you can transform. Let's say you can call n1 direction x prime direction, right? And you can call n2 direction y prime direction, right? Now assuming this is a string at a point in x, y, z coordinates. This is a strain at a point in that. It's a tensor. And then you define another coordinates, which x prime, y prime, and z prime. If you rotate this string tensor into the x prime, y prime, z prime direction, then you will have the strain in that coordinate system. Let's say you rotate this thing to a new coordinate system, and you have ex prime, y prime, which is a bunch of numbers right here. All right. This first number is what we're seeking for part A. After you rotate over, this first number is normal strain in the x prime direction, n1 direction, n1 as x prime. This is epsilon x prime, x prime. Are you all with me? Now, what do you say this number is? The second number in that matrix. That's epsilon x prime, y prime. Right, that's epsilon x prime, y prime. So what is that number? That number is the answer to part B. Right? So basically, rotating, transform this string tensor into a new coordinates. You do that operation, it solve this two parts altogether. You just pick out the two elements out of that matrix after transformation. All right, any questions? All right, now let's look into details. How do you transform that strings? We learned how do you do string transformation with a set equations. What do you call that? We call it stress strain. Not this one. Yeah. Strain relationship. Like this one. This one. Not this one. That one. All right. So this is you can transform a string tensor from one coordinate to another coordinate using this matrix here. Okay. You just multiply to the right and to the left in this matrix. The T is transpose. All right. And this transform matrix, this first column here is basically the direction cosine of x1 prime with respect to x1, x2, x3. Okay. Now that essentially is this vector here, this three number. Now if you look at it, this is direction cosine of the x prime axis. We call n1 x prime, so that's it, right? And then the second column of the transform matrix is the direction cosine of the second matrix, second direction, x2 prime, is this, right? This three. Okay. Now the tricky thing about this problem, the third one is not given. You don't need this thing, but you can cook up some arbitraries that just ensure they're perpendicular to 1 and 2. But I'll show you, you don't really need to know this. You can calculate how this without really need to know this. So let's go back to the calculation here. So we have this matrix. We have this matrix. Let's construct the E matrix. It's here. It is what is the number? 1 1 minus 1 1 1 2 minus 1 2 2. Minus 100 200. What's the number here? 200. Now I'm going to construct the N matrix. N matrix is first column is the first three number in that thing. This number 2 1 2. 2 1 2. Right? That's first column. The second column is this number. 0.25 0.94 221. 942. Blah blah blah. This I don't care this number. All right. Now, NT matrix. What is NT matrix? NT matrix is the transpose of this. 2, 3, 1, 3, 2, 3, minus 0 0.25, 0 0.942, minus 0 0.221, and right. And the new string tensor is NT multiplied E matrix with 100, 100 minus 100, 100, 100, 200 minus 100, 200, 200, multiply this matrix. Okay. All right. So this equal to a matrix E prime, this EX prime, X prime, EX prime, Y prime, because we only care about these two numbers. All right. So you can prove easily that this number equal to this matrix, multiply this vector, and then multiply this vector. And this entry is this matrix multiply this vector and then multiply this vector. Okay. So you can calculate that. You basically just calculate this multiply this this matrix multiply 3 by 3 matrix by 1 3, you got 3 by 1 matrix, and then this 1 by 3 matrix multiply 3 by 1 matrix, you get 1 by 1 matrix, and that will be this number. Okay. Similarly, you can prove that this is this number. You just go ahead and calculate, and you can figure out these two numbers. Okay. So I actually calculated over here. I can tell what the number is. Where is that? All right. So it turns out that the EX prime X prime is 196 7 micro. Okay. EX prime Y prime is 213.05 micro. That's the part 1 and 2. Okay. Now remember, what you calculate is the shear strain tensor form. Okay. Which one? So this is not a gamma X prime Y prime. So this actually equal to half. So if you want to answer gamma X prime Y prime is 2 times. Okay. So the gamma X prime Y prime, it really is 426.1 micro. That's gamma X prime Y prime. All right. That's a solution to part 1, A and B. And the normal strain in the direction defined by X1 is just this number right here. All right. Any questions? Comments? Okay, let's keep going with the second part. Find the principal strain and the maximum shear strain. It's this is again that part is it just find eigenvalue, eigenvector of that matrix. It's pretty straightforward if you know how to use certain package to do that. So I can so E1 is 400 micro. E2 is 200 micro. E3 is minus 100 micro. I couldn't find where the principal direction is. What I got here. All right, I have to redo the calculator because I think I lost the principal direction. But anyhow, this is 3 eigenvalues. Now, what is the maximum shear strain? Remember, maximum shear strain is the largest difference. Max E1 minus E2, E2 minus E3, E3 minus E1. The maximum difference between the 3 eigenvalues. So it's pretty straightforward because you don't need to calculate the largest difference between the normal strain of these two. So max of this equal to 500. Is different between these two. That's the maximum shear strain, micro. All right, that's this part C. Okay. Part D is find volumetric strains. Volumetric strain is the sum of 3 principal strains. Okay. Volumetric strain is is 400 plus 200 minus 100 equal to 500 micro. Volumetric strain also is the trace of the strain tensor. Strain tensor is 100 minus 100, 100, 200, 200, minus 100, 200, 200. The trace of the tensor, a tensor is the sum of the diagonals. That also equal to 500. So that's the same as this. This is one of the invariant of matrix. You can cross check. So this this E volume should be this. The sum of 3 principal strains should equal to the trace of the matrix. All right. So you can decompose a strain tensor into 2 parts. One is signify a uniform expansion. Each of it is 1/3 of EV, uniform expansion in 3 directions. Plus the balance. This balance is called the deviatoric strain, DEV. This is E, total strain. So this signifies a uniform volume change, equal volume change in all directions. That's the strain tensor. So we have this strain tensor here, which is 100 minus 100, 100, 200, 200, minus 100, 200, 200. So you can easily calculate the deviatoric strain. You just subtract this out of this, right? So this deviatoric strain, DEV, this strain equal to, so 100 minus 1/3 of this 500, right? You just subtract. All right, so it's minus 66, minus 60.7. This is 33.7, 100 minus 100. This one 100. This is 33.3. It's 200 minus 100. 200. 33.3. This is a deviatory string component right here. The unit is micros. You just subtract this part out of this part. Okay. Yeah, that's this 3 problem. Any questions? Comments, questions? All right, there's no more questions. Let's go over homework number 1, the solutions. Open up homework number 1. All right, this is about stress. So we have stress tensor here, this part. We have a direction. Want to calculate the traction in that direction, the traction, and find a normal stress at that cut. So basically, essentially you have coordinate system. You express the strain tensor in this coordinate system. You cut it at certain orientations. The orientation is defined by this vector n, which is this vector. You find a traction on it. Now, traction is not necessarily perpendicular, same direction as that, but we learned from it's an equation called Cauchy equation. The traction at any cut is tensor times the vector in that direction, right? Traction is a vector. So this is 3x3 matrix times 3x1 matrix. You add up a 3x1 matrix. All right, this is a vector. This is a force vector. And then to find a normal, you basically dot t to the n direction. You basically project t to the n direction. And then you multiply. And this is scalar. This is a fraction of t in the n direction. This is unit vector. So this represents the normal stress on that cut. So this is a high level solution, but to solve it, we need to calculate. So I have calculated. Over here, actually, I used the Excel. Oh, not this one. All right. So this is the S matrix. Make it a little bigger. Can you see? Can you see this? How do I make my screen bigger? All right. So, thank you. This is the S matrix. This is the stress matrix. This is my vector, n vector. I essentially just multiply this matrix by this vector. This is my traction vector, by the way, T. T is S multiplied N. Right. And then I further dot T with N. I made a dot product. And this is a normal component of that fraction. It's 3. The direct and normal component obviously is N. So that's pretty easy. This is part 1. This is solution. Any questions? All right, now let's go over problem number 2. Problem number 2 is about stress transformation. You basically transform stress tensor from one coordinate to another coordinate. Now these n vectors are there. So this is a this old coordinates x, y, z. The new coordinates divided by the 3 new vector x prime, y prime, z prime. This 3 number is the direction cosine of this vector, all right? And this 3 number is the direct cosine of the y prime axis, and this is the direction cosine z prime axis. This is z prime, that's y prime. So all we need to do is basically exercise the equation x prime at nt Sn, right? The equation that we learned about in this. The same equation applied to both stress strain, right? We just use this equation. So you just construct the right equation. Just remember the way to construct, and every column is a vector represent the direction of new axis. This 2 and 3. That's all that's important. Once you remember this, it's just pretty simple. What is that right here? I calculated with again Excel, pretty easy. So I constructed the n matrix, this n matrix. This is my S matrix, and this is the transpose n, and they multiply all together. NTSN, this is the matrix after transformation. So Excel is pretty convenient to do matrix multiplication. The downside of Excel is that Excel doesn't have a intrinsic function to calculate eigenvectors, which is a pain. You had to write a little bit of a code to do that. But anyhow, that's the first part of the question. Calculate this new stress vector in the new coordinates, which is equal to that. Actually, that's all the problem is to calculate that. Okay. Any questions? All right, now let's go over the third problem. The third problem is essentially the same as as principal strain problem. It's just different context. So essentially, the principal stresses for this stress tensor is the 3 eigenvalues of this matrix, and associated with each eigenvalue, there's a principal direction, which turns out to be the eigenvectors associated with the eigenvalue. So you just need a package that can calculate eigenvector, eigenvalue with a matrix, right? And then you pick the largest one. The largest eigenvalue will be the maximum tensile stress, right? You can rank them. Now there's association. Each eigenvalue is associated with eigenvector. All you need to do is find a package that has this function to type in these. So let's do these calculation. Excel doesn't have it, so I typically use Sage Math. Let's get started. We'll try to calculate this problem. All we need to do is type in that 3 by 3 this matrix and ask Sage Math to do the rest. And then you get a result and interpret what does it mean. All right, start it up now. Just start a new one. Sage Math, okay. It takes a few seconds for it to start up. Kernel starting, please wait. Let's wait for a little while. All right, 802.051.214. 802.051.214. Still starting. All right, started. Let's do a test. Let's do a 1 + 1. See if you calculate right. Excellent. All right. So my define S is equal to matrix QQ. I just type in that matrix basically. 832. 832. That 802. 0, 5, 1, 2, 1, 4. Show. Yes. 802, 0, 5, 1, 2, 1, 4. Let's see, that's right. Yeah. Okay. So I can do S dot right here. S dot eigen values. So that's 3 eigenvalues. I can do S dot eigen vectors. Right. All right, so these are eigenvectors. All right. Blow up a little bit. So you see there's association relationship. The first eigenvalue is this one. This parenthesis is the eigenvector associated with it. And this is the order of it. So you can ignore this one. This one doesn't mean anything here in this context. And this is second eigenvalue, and this eigenvector associated with that one, the third eigenvalue. You can see the highest one is 8.8. That will be your sigma 1, the highest. Usually we rank them based on the values. The second value is 5.35, right? The third one, 2.78. And the direction there. You can prove that these eigenvectors are orthogonal. Oh, not this one. So part B, so our answer to this problem, what is the maximum tensile stress is a point. Where is that? Did I close it? Right here. Right here. So the highest tensile stress is 8.868, this number. And this is a normal perpendicular to that plane, right? This last row is our answer for the second part question. Okay. Any questions? All right, if there are no questions, I'm gonna stop here. I'll see you guys, I guess on Monday. Is that Monday? Yes, Monday. Okay, you all have a good break. No, on Friday, sorry. We have a session on Friday. I'll see you guys on Friday. We're gonna do some CLT calculation together. Make sure you get a version of CLT code ready by that time. So I'll meet you on Friday, same time. Okay. All right, have a good day. Bye-bye.